Hi, welcome to the lecture on quantum static simulation. My name is Ieva. I'm a research staff member at IBM Quantum, and for my research, I focus on quantum computing applications for chemistry. So I am super excited to give this lecture today. Chemistry is considered to be one of the most promising applications of near-term quantum computers. And that is because a quantum computer can, in principle, prepare and store richer many-body wave function representations than classical computers. Long story short, chemistry arises from electron and nuclei interactions in atoms and molecules, and these interactions are governed by the laws of quantum mechanics. So it is very advantageous for us to use a quantum computer with quantum properties to perform relevant chemistry simulations. Quantum computers can enhance the type of simulations we can perform, and they promise to solve problems that are, quite frankly, unsolvable on today's classical computers. So the main goal of today's lecture is to explore one type of chemistry calculations that we can do on today's classical computers, which are classified as time-independent or static. So it is absolutely essential to start this lecture with the wavefunction formalism. So this is probably a brief recap or overview of what you have already learned in earlier lectures of the summer school. And so molecules in chemistry can be described by quantum mechanical equations. And more specifically, the properties of a molecule are determined by the so-called wave function. A wave function is a function of position at a given time, and it contains all the measurable information about our system of interest, and most importantly, it allows for energy calculations via the Schrodinger equation. Now, our wave function of interest lives in a multidimensional Hilbert space, and in fact, it's very computationally challenging to really explore the whole of Hilbert space. So what we try to do, we in fact try to introduce a bunch of reasonable approximations and to essentially reduce the dimensionality of this vastly large Hilbert space. So one way to achieve this is to use separation of variables, which essentially allows us to rewrite our wave function as a product of two functions, each of which is a function of one variable only. So as depicted here, separation of variables allows us to write our wave function as a product of two functions for position and time respectively. And so with separation of variables, we are transforming a multidimensional problem to a set of small one-dimensional problems, okay? So the position dependent wave function solution is also referred to as a stationary state with all observables independent of time. Stationary states are very important in quantum mechanics. They define the total energy because they are the eigenvectors of the energy operator, and we'll talk about that in just a few slides. But this is not it. There's in fact more approximations and simplifications that we can do at this stage. And in fact, we can separate the electronic and nuclear degrees of freedom as it is described by the so-called Born-Oppenheimer approximation. So the Born-Oppenheimer approximation essentially neglects the motion of the atomic nuclei when describing the electrons in our molecule. And that is because the magnitude of the acceleration is inversely proportional to mass as we know it. And so the acceleration for much lighter electrons is large, and the acceleration for heavier atomic nuclei is small. And considering that, we can end up essentially neglecting nuclei and consider them as stationary. So our stationary wave function, as depicted at the bottom of the slide, can be further rewritten as a product of two functions that depend on nuclear and electronic positions, the former of which can be neglected. So at this point, with all of these approximations, our molecular wave function depends on the electronic part only, which is the solution to the electronic Schrodinger equation. Schrödinger equation is the central equation in quantum mechanics that describes the quantized energies of our system. So essentially, we are solving an eigenvalue equation as depicted here, where we have our Hamiltonian operator acting upon the wave function and extracting the energy associated with our system. The Hamiltonian operator is composed of the kinetic and potential energy operators as shown here. And for the kinetic energy part, we're only considering the electronic kinetic energy. But for the potential energy part, we have several terms that we have to take into consideration. And that is the electron nuclei attraction term, the electronic repulsion term, and then we have a constant that essentially stems from the Born-Oppenheimer approximation. It describes the nuclear potential energy, which we can approximate as a constant here. And so by solving the Born-Oppenheimer-Schrödinger equation, we can construct a lot of useful properties in chemistry that we can then utilize for our studies. One of an extremely useful piece of information that we can get is the construction of the potential energy surface. So potential energy surfaces are created by determining the electronic energy of a molecule while varying the position of its nuclei. And so in the picture here, you can see that in fact, we're looking at two different surfaces that are separated by an energy gap. The lower surface is the so-called ground state potential energy surface, and the higher surface is associated with higher energy excited states. And so by studying these surfaces, we can get insights into chemical reactivity and understand why some reactions proceed in a specific way, resulting in specific products. These surfaces map our reactants, our intermediates, transition states, as well as our products. And for example, excited state surfaces are extremely important in photochemistry and in any branch of chemistry that really considers excited states, for example. So this is pretty much it. In ab initio quantum chemistry, in computational chemistry, we're putting a lot of effort to solve the Schrödinger equation and to get the information about our molecular system and its associated potential energy surface, electron densities, vibrational frequencies, and so on and so forth. However, there is a big challenge to consider, and the challenge is that the wave function of interest depends on the coordinates of all the electrons in our molecule. And the number of variables that we have to consider actually increases exponentially with the size of our molecular system. In fact, for any chemical species larger than the hydrogen atom, only an approximate solution exists. And in other words, in its exact form, the Schrödinger equation is not solvable. And approximations have to be made, and we have to use numerical methods to really try to solve this Schrödinger equation. And in fact, there is a plethora of quantum chemistry methods, such as density functional theory, wave function-based methods, and you probably learned about some of them in previous lectures. But one important relationship to keep in mind is the simple relationship between computational cost and accuracy of our calculations. And so you can see that as we are growing in accuracy, we're actually growing in computational cost, and some really accurate methods such as ab initio or wave function based quantum mechanical methods have very high computational cost. And so one thing to note here is that probably the most widely known method, such as density functional theory, is important to highlight because this method provides relatively high accuracy for relatively low computational cost. And so, why do we care about accuracy so much? Why do we want to have these really precise and accurate calculations for chemistry? And that is because if we want to predict something as intuitive as reaction rates, for example, we really have to do these calculations with very high chemical accuracy. And this chemical accuracy has to be around 1 kcal per mole. Just to give you a little bit more of intuition here, in order to predict, for example, reaction rates, we have to know the activation barrier associated with our chemical reaction of interest. In other words, we have to know the energy difference between the transition state and the reactant molecules. And so that energy gap is the so-called activation energy barrier. And so as our reactants climbing to reach the transition state, they have to really get over that activation energy barrier for the reaction to proceed. And so if we are not able to calculate this activation barrier accurately, we will have exponential errors in our reaction rate predictions. Okay, so this is extremely important. And in 1982, Richard Feynman suggested that potentially we need to rethink how we do simulations of systems in chemistry. And more particularly, he proposed that we have to use a quantum system to simulate other quantum systems in chemistry. So in essence, we need quantum computers that can use quantum systems themselves to store and process data. And so the idea here is that we take our chemical systems and we map them onto quantum computers that are composed of qubits and quantum gates, and then we do some measurements to extract important information such as the ground state energy associated with our system. Okay. In fact, before we do this straightforward mapping, there is a mathematical model standing in a way. We have to take our physical system, we have to mathematically model it, and we have to map it onto a quantum computer. And an important thing to consider here is that our mathematical model has to be rewritten or expressed in a second quantized representation. So, how do these mathematical models work? Well, an important thing to consider here is that we have to essentially break up our molecular space into basis functions that essentially approximate our molecular orbitals. And we can choose these basis functions in a very large number of different ways. For example, we have Gaussian bases that are commonly employed in molecular simulations due to their compactness, while we have plane waves, and they are mostly used in the simulation of crystalline solids, for example, right? So these functions essentially represent our molecular orbitals, as I mentioned, and they describe the location and wave-like behavior of our electrons. In fact, as shown in this picture, each of these individual orbitals can be occupied by 2 electrons, one spin up and one spin down. And according to quantum mechanical rules, electrons populate these orbitals starting from the lowest and climbing up. So in our mathematical model, we consider orbital occupation as shown in these parentheses. So if our molecular orbital is occupied by 2 electrons of opposite spin, our occupation here would be 1, 1. If our orbital is only half filled, meaning just with 1 electron, then our occupation would be 1, 0. We also see the 2 pictures here that depict the highest occupied molecular orbital of caffeine and the lowest unoccupied molecular orbital of caffeine. And you can see that essentially these orbitals show the highest probability of where electrons can be found. So with this sort of occupation representation, we arrive to an important concept in quantum computing, and that is expressing our Hamiltonians or our mathematical models in the so-called second quantized form. So second quantization is an occupation number formalism used to describe quantum many-body systems. And when we use second quantization, we essentially ask our key question, which is how many particles do we have in every state? And so typically when I teach second quantization to people who have never heard about it before, I want to emphasize that the essential information here consists of the occupation number of each single particle state, as well as the anti-symmetry of the state under particle exchange. Long story short, you can think of this as we are taking our fermionic Hamiltonian and we are rewriting it, or sorry, we're taking our molecular Hamiltonian and we are rewriting it in its second quantized form, which is essentially a more compact and just a more useful form to rewrite our molecular Hamiltonian to. And so you can see that our wave function is essentially a sum of different Fock states. It's a linear combination of Fock states, and these Fock states essentially have our particle number representation. This representation, second quantization, also considers the Pauli exclusion principle, which states that identical fermions cannot occupy the same state simultaneously, which applies to the fact that we are considering electrons in our simulations. Besides that, the second quantization method involves the use of the so-called creation and annihilation operators. These operators respectively create and annihilate particles in specified single particle states. It's sort of important to just keep track of where are we creating and where are we annihilating particles. We can also think of it as hopping, for example, where particles are hopping between different states, or we end up creating and destroying them. So we're not going to get into too much detail of second quantization, but what's really important to note here is that our molecular Hamiltonian, as we wrote it at the beginning of this lecture, has all these multiple terms that describe kinetic and potential energy of our system. And now we have to rewrite it into a more compact form, which is the so-called second quantization form, to get our fermionic Hamiltonian. And now you can clearly see that this fermionic Hamiltonian expression has creation and annihilation operators acting on specific states, as denoted here by P, Q, R, and S. And in addition to that, we have these scalar components here that are Coulombic overlap and exchange integrals determined by the basis set chosen. The first term is a one-particle operator, so we generate excitations for a single particle. And then the second term is the so-called two-particle operator, and so again, we generate excitations for two particles at the time. So we end up destroying two particles in some states, but then creating two particles in other states. Now that we have our Hamiltonian written in its second quantized form, we can easily do one more step needed before we can put it on a quantum computer, and that is we have to rewrite this Hamiltonian into a more natural form for quantum simulation of electronic structure on a quantum computer. So the basic idea here is to replace each fermionic operator with a tensor product of Pauli matrices. So each Pauli matrix here is indicated by a sigma, and it will be acting on one qubit. So each Pauli operator is acting on one qubit, and here the coefficients denoted by lowercase c represent real scalar coefficients that depend on these 1 and 2 body integrals that we discussed in the previous slide. As we do this type of transformation, we say that we are essentially mapping fermionic Hamiltonians onto qubit type of Hamiltonians. And there are different types of mappings that we can employ. And a lot of times in literature, you will hear about parity mapping, Jordan-Wigner mapping, as well as Bravy-Kitaev mapping. These mappings are essentially problem dependent, and a lot of times you have to consider the problem in hand before you decide which type of mapping you would like to employ. But just to give you an example, a very intuitive way to map chemistry problems onto quantum computers is by utilizing Jordan-Wigner transformation. And again, here at the top of the slide, we see the fermionic Hamiltonian written in terms of rising and lowering operators. And we see that the Jordan-Wigner mapping would redefine rising and lowering operators in terms of Pauli matrices, as shown here. And so we end up rewriting our Hamiltonian. This sort of rewriting is necessary because essentially electrons are indistinguishable particles, whereas qubits are distinguishable. And so to really abide by the quantum mechanical rules, we have to do these specific types of mappings. So now that we have our Hamiltonian in a computational or qubit basis, we are essentially ready to run our quantum simulation and retrieve the ground state energy associated with our system. In fact, we use the variational quantum algorithms to approximate Hamiltonian eigenstates and eigenvalues on quantum computers. So variational quantum algorithms typically operate by preparing the parametrized trial state, also known as Ansatz, on a quantum computer, execute our circuit, measure the obtained state, and then we end up updating these parameters according to a classical optimization algorithm to really make sure we are converging to the ground state energy associated with our system, okay? So the initial wave function, as shown in this slide, has to be parametrized, and we achieve that by applying a parametrized unitary to an initial wave function. And then, again, as I mentioned, by iteratively updating these parameters and by measuring the energy, we are able to converge to the ground state energy of our system. So now with this big picture in mind, let's break this process into smaller steps and let's try to build our intuition between each step of importance. So, the ground state energy, first of all, is extremely important in quantum chemistry. We use ground state energies to calculate many other properties associated with our chemical reactions, such as reaction rates or reaction pathways that again would give us intuition as to why some products are forming or as to why some side products are forming. And VQE, which stands for Variational Quantum Eigensolver, allows us to find an upper bound of the lowest eigenvalue of a given Hamiltonian. So let me try to explain in very simple terms what's going on. So when we have our Hamiltonian, and when we know the eigenstates associated with our Hamiltonian, then we can easily solve the eigenvalue equation, and we can get the associated eigenvalues as depicted in the first bullet point. So for the eigenstate associated with the smallest eigenvalue, we would get the ground state energy. So the problem here is, or the challenge is that we don't really know the eigenstates. We only know our Hamiltonian. But we also know that if we take an arbitrary state with an associated energy, we know that that energy that we get for an arbitrary state will always be higher or equal to the ground state energy. So we essentially get an upper bound for the ground state energy, and that's exactly what we want essentially. So the problem or the challenge here is that just knowing the upper bound doesn't really give us much benefit, right? The closer the upper bound is to the real value, the better. So in principle, we could try to sample all the possible states that live in this Hilbert space and then end up picking the one with the lowest energy. However, that is not practical at all because there are just way too many states, and to really accomplish measuring all of them would just not be reasonable. So, most of the states will also give you bad answers, so there's really just pointless in trying that. So what we have to do is we essentially have to build a parametrized quantum circuit, and we have to essentially start with some sort of parametrized trial state, also known as Ansatz, which will essentially be our approximation to the ground state energy. And then this parametrized Ansatz or parametrized trial state will be optimized until we get to the state that gives us the ground state energy associated with our system. So now that we know a lot about our Hamiltonians and we know a lot about our Ansatz, we can sort of put all these pieces together into this summary as shown here. So an electronic Hamiltonian has to be written in its second quantized term form. The first term corresponds to single electron excitations, and the second term corresponds to two electron excitations. The H sub PQ as well as H sub PQRS are 1 and 2 electron integrals that are essentially computed or pre-computed on a classical computer. And then this Hamiltonian has to be mapped onto the Hamiltonian of distinguishable qubits by using one of the three common mapping techniques. And we specifically highlighted Jordan-Wigner mapping as a great mapping for, or intuitive mapping for chemistry problems. But regardless of the mapping of your choice, the resulting qubit Hamiltonian can be written as shown here, which is essentially just a bunch of Pauli matrices. And we also have these scalars alpha here, which essentially depend on our one and two body integrals. So at this point, we are ready to run our variational quantum eigensolver. We prepare our parameterized ansatz on a quantum computer, and we execute a circuit. Then we measure the obtained state, as shown by this equation here. And then we update our parameters theta according to a classical optimization algorithm. But the idea is to run the circuit as many times as possible, or to do this loop as many times as possible until we achieve our desired ground state energy, right? So basically the quantum computer is used to measure energy here. And again, in addition to all the individual terms that have to be measured, we have to make sure that we are really measuring enough times to build up sufficient expectation value statistics. In fact, for practical chemistry simulations, we need very long coherence times and access to deep circuits. Depth here is referring to the number of layers of gates that cannot be executed at the same time. And essentially, long coherence times are needed to maintain the entangled quantum state. And so today's quantum computers are characterized by relatively short coherence times. And so to really do useful chemistry simulations, we have to think about how can we potentially cut down on computational costs? How can we save on resources? And more specifically, in this lecture, I wanted to focus on two major aspects that people do a lot of research on, and that is our Ansatz selection and our Hamiltonian construction. So Ansatz selection is a central part of the VQE stack. As we discussed, choosing the right ansatz is essential to guarantee that the final solution is close to the global minimum. On the other hand, Hamiltonian construction takes into account the whole orbital space, right? And so the strategy here is to try to potentially reduce that space by choosing orbitals in a very smart way to make our Hamiltonian as simple as possible. And again, all of this is done to really cut down on our computational costs. So let me first focus on Ansatz selection, and let me just describe what sort of desired Ansatz we ideally want. So for an efficient Ansatz selection, it is essential to maximize the chances of this Ansatz covering parts of the Hamiltonian space that contain our solution of interest, and that is uh, that space where a state that is sufficiently close to the desired state, which minimizes the expectation value of our Hamiltonian, right? So we want our ansatz, therefore, to be expressible. We want to have circuits that have small number of qubits that are short in depth, which means we don't want to have too many operations per circuit. And we also want these circuits to be hardware efficient. And that is especially important because we want these Ansätze to be favorable to near-term noisy quantum devices that we have today. Again, when we try to estimate the cost of our ansatz, we typically take into consideration circuit depth, which refers to the number of layers of gates that cannot be measured, that cannot be executed at the same time. It's important to consider circuit connectivity. Let's say some qubits can, so it's very important to sort of keep in mind the architecture of our device. We have to consider the total number of parameters, the total number of 2-qubit gates, as well as the gate type. And so two widely used classes of Ansätze are hardware efficient and chemistry inspired Ansätze. And again, there's a lot of research that people do trying to create more efficient Ansätze that span the right Hilbert space and just cut down on computational cost. But let me walk you through the two different major types of Ansätze. And so hardware efficient Ansätze, as the name speaks for itself, uses quantum gates that are quantum device friendly and essentially tailored to the quantum device. But the issue that arises with these type of Ansätze is that they span a very large portion of the Hilbert space, which makes our computations very inefficient. Because they span a very large portion of the Hilbert space, they also require a very large number of parameters to be optimized, which again increases our computational cost. Now, chemistry-inspired Ansätze, one of which is quantum unitary coupled cluster Ansatz, is pretty much mimicking full CI level results, and that is very exciting. It's inspired by exponential Ansätze, as shown here. We use operators that generate single and double particle hole excitations, which again populates the orbitals in the right way. This Ansatz is not hardware efficient, and very deep circuits are essentially needed to really execute the simulation with this type of unitary coupled cluster Ansatz, for example. What typically happens is that in many studies, we use unitary coupled cluster Ansätze to do simulations, and then when we go on quantum hardware, we try to use hardware efficient Ansätze, just because we have to make sure that it's sort of friendly to the existing quantum devices. Now let's switch gears and talk about how we can choose orbitals in a smart way to make our Hamiltonian simulations simple. And again, the goal here is to really cut down on the computational cost. And so for different Hamiltonian strategies, we have to remind ourselves that our Hamiltonian is expressed in the second quantized form, and it's composed of two major parts, that is the one particle excitation operator and the two particle excitation operator. And again, it has these coefficients that essentially describe the 1 and 2 body integrals. And these integrals contain some of the spin orbital information as shown here. So our task here is to really try to pick these orbitals in such a way where we really just choose the orbitals that participate in, let's say, some sort of bond breaking or bond making processes that govern the reactivity of our system. And we can end up dividing a set of these orbitals into an active set of orbitals and inactive orbitals, and then sort of like distribute them on quantum and classical computer respectively, and in such a way cut down on the computational cost. So with that, we can define our active space, where we choose our orbitals and electrons that are the most important for an adequate description of our wave function. So as depicted in the slide, you can see that some core orbitals that are fully occupied by electrons can be sort of kept frozen or semi-disregarded because they don't participate in, let's say, bond breaking or making processes. Then let's say we pick some orbitals that are partially occupied or fully occupied, perhaps even empty, and call them our active space orbitals. And then there are some also external orbitals that are much higher in energy that are empty, and again, perhaps we don't really need them to be taken into consideration. And so by dividing our space into core orbitals, active orbitals, and virtual orbitals, we can start thinking about how perhaps core and virtual orbitals can be approximated by cheaper computational methods, whereas active orbitals could be mapped onto quantum computers and calculated from first principles. In fact, stemming from this idea, there is a different branch of research called quantum embedding, which makes the computational process less demanding by dividing a very large computational and molecular space into smaller, more manageable subsystems, as shown into this that active space is so mapped onto a quantum computer, and then let's say all the orbitals that are less important can be calculated using classical computer, and so then we can combine the two results and really solve some memory and convergence issues a lot better. We can study much larger systems, and we can also get our results in a much more efficient way. So essentially, the bottom line here is that the active space selection scheme distributes the workload between classical and quantum computers, and that really allows us to do our calculations in a much more efficient way. So now that we talked about Ansatz selection strategies as well as Hamiltonian construction strategies, I want to briefly touch upon another very important aspect of running VQE calculations, and that is parameter optimization strategies. So as mentioned in previous slides, we have to optimize our parameters and just slightly change them so that the energy is allowed to converge. Again, there are different optimizers that, let's say, you would find if you open the Qiskit textbook and looked for what sort of optimizers are available. And again, the existing optimizers could be semi-broken down into two big subgroups, and that is local optimizers that essentially searches the neighborhood for a candidate solution, and then global optimizers that essentially explore all the possible solutions. So again, you can probably intuitively agree with me that local optimizers are perhaps more efficient. They search smaller space but find candidate solutions much faster. And so there are different types of local optimizers, and they range from Kabila, conjugate gradient, gradient descent, SPSA, and so on and so forth, and then other global optimizers. So again, when you run your simulations, you can really play with many different options, and you would see that some optimizers are actually much faster, others take a longer time. But essentially, you really have to, again, sometimes tailor these optimizers for your problem of interest. So another very exciting thing about running VQE calculations is that we can end up having extension of VQE to excited state energies. Again, this is bringing us back to some of the initial slides that we have looked at. And so besides calculating the ground state energies associated with our systems, we are sometimes interested to know what sort of excited state energies can we obtain. And so excited state energies are again very important in photochemistry, in fluorescence and phosphorescence studies. We, let's say, shine light on our molecular systems and excite them to higher energy levels from which they then decay or transfer energy to other molecular nearby systems. Again, this has a lot of applications in solar materials design and other and energy transfer systems. So again, we essentially excite our molecules, and that allows us to predict some interesting photo-induced reactions that have a lot of applications in different technologies. There are two excited state energy methods that I encourage you to explore using Qiskit. Both methods inherit the benefits of variational approaches from ground state calculations. So we're essentially using the information from VQE ground state energy calculation to really obtain the excited states. And the two methods I would like to highlight today are the quantum subspace expansion, also known as QSC, or quantum equations of motion, also abbreviated as QEOM. So while a quantum subspace expansion algorithm calculates the energy values of the excited states themselves, the QEOM algorithm calculates the energy difference between the excited and the ground states. So again, you can use both algorithms, maybe compare and contrast, but ideally you would get pretty much the same energy for the excited states, except in one case you get the actual excited state energies, in another case you get the difference between the excited state and the ground state energies. The advantage of quantum subspace expansion algorithm relies on the fact that it can be implemented in a very straightforward way. So as I mentioned, it's simply an extension to the VQE algorithm, and it doesn't require any modification of the quantum circuit, but just some additional measurements that we have to do of some additional matrix elements of the ground state wave function. And so as indicated here, we consider the Hamiltonian of our system as well as this additional overlap matrix that we look at. The quantum subspace expansion algorithm is inspired by a classical method called CI singles, which is commonly used in conventional quantum chemistry. On the other hand, the QEOM algorithm is more resistant to computational noise. And so, again, it's building on our VQE calculations, but the only thing that we have to do in addition is to compute the additional matrix elements denoted as M, Q, V, and W. And so from these additional measurements, we can solve the secular equation as shown here. And we can use this equation to really get the excited states of interest. So there is a lot of simulations you can do using Qiskit Nature. In summary, today we explored some of these electronic structure calculations we could do, as well as the excited state calculations we can do. But of course, there are many more functionalities that you can explore in Qiskit Nature. And as a summary, I also wanted to just walk you through how a typical quantum chemistry problem would be sketched in Qiskit Nature. And here we see different steps going from the actual problem definition, second quantization, qubit converter, qubit operators, then choosing a quantum algorithm, and then retrieving results. We spend a lot of time in today's lecture looking at how we construct our problem, and that is going from our molecular system, constructing its Hamiltonian, looking at how that Hamiltonian can be mapped, and then choosing our variational quantum algorithm to really obtain the ground state energy of our system. But typically, before you even begin with your Hamiltonian construction, you have to have the coordinates associated with your molecular system. You have to define the geometry, spin, and charges associated with your system. And then you have to choose your electronic structure driver, which is essentially a classical code, such as PyCF, for example. These drivers are important because they act they do some classical calculations that then help you to really construct your Hamiltonian of interest. Some of the really cool functionalities to mention here is that Qiskit Nature has something called transformers, which can allow you to select the active space of interest. Again, that means by choosing some really important orbitals that would allow you to cut down on the computational cost. And really maximize your efficiency. And then once you have those pieces and components all together, you can set up your fermionic Hamiltonian in terms of fermionic operators, and then proceed through the whole chain of steps as we discussed in this lecture. And with that, thank you so much for your attention, and I hope you enjoyed today's lecture.